before we move on to chapter 5 on the probability distribution, let's quickly review the combination and permutation. I get to complete that last time. Permutation. Okay, so this example, the board of trustees of college has 9 members. Each year, a 3-person ethics committee is chosen. At the same time, the board elects 3 officers, president, vice president, and secretary. How many slots of candidate for officers are possible? So let's take a look at this. In order to elect the officer, you need to pick 3 members out of total 9 members. So pick 3 officers from 9 members. And here, each one of them get a different title, so the order matters. So we know this is definitely a permutation. We do 9p3. So for the permutation formula is n factorial over n factorial. So it's going to be 9 factorial in this case. N equal to 9. Here n equal to 9. X equal to 3. Okay, so it will be I equal 3. So that will be n factorial over n minus r factorial. So it will be 9 factorial over 9 minus 3 factorial. So it becomes 9 factorial over 6 factorial. So this will be 9 times 8 times 7 times 6 all the way to 1. 6 times 5 times 4. So we cancel everything after 6. Multiply 9 by 8 by 7, you get 504. So you have 504 different slots of candidates for office as possible. If you look at part B, now you're just picking 3 committee members. So pick 3 committee members from 9 members. And the order does not matter because each one of them will share the same title. They're just committee members. None of them have special title. So that does not matter. I know this is definitely a combination. So it becomes NCR will be n factorial over r factorial times n minus r factorial. So here will be 9c3. So it will be 9 factorial. N equal to 9, I equal to 3. Okay, the 3 factorial times 9 minus 3 factorial. Again, we're going to expand it. So 9 times 8 times 7 times 6 all the way to 1. And the other one, this is 6 factorial. 6 factorial is 6 times 5 times 4 times 3 times 2 times 1. We also have 3 factorial. So 3 times 2 times 1. Okay, again, we cancel everything after 6. And then 3 go into 9 3 times. 2 go into 8 4 times. Turn out to be 12 times 7, 84. So we have 84 possible combinations to pick 3-person ethics committee. Okay, so just quickly review the combination permutation here. Now let's move on to chapter 5, probability distribution. Probability distribution gives the probability for each value of the variable that's determined by chance. So let's try to distinguish between the outcomes that are likely to occur by chance and the outcomes that are unusual in a sense and not likely to occur by chance. So let's take a look at random variable. A variable typically represented by x that has a single numerical values, determined by chance and for each outcome of the procedure. For example, let's say you pick flip a coin 2 times. So we end up with a, let's say, concentrate betting on and then bet on number of heads. Then here you may have a 0 head, 2 tails in a row. First possible outcomes, 0 head. Second possible outcome, 1 head. Third possible outcome, 2 heads. And if you look at all of these outcomes, is a single, either 0 head or single numerical value. And then all of this determined by chance for each outcome procedure. Right? Each outcome has different probabilities. So all the possible outcomes could be head, head tail, tail head, or tail tail. That means 0 head will be 25% of chance. So you have 25% of chance for 0 head. Okay, 1 head will be 50% of chance. The middle 2 are 1 head, 50% of chance. And then 2 heads, you have 1 over a quarter of chance, so it's 25% as well. 2 over 4 and then 1 over 4. Okay. That exactly explains what's a random variable here. And probability distribution is the distribution that gives the probability for each value of the random variable. Okay. Often expressed in the graph table and formula. Discrete random variable either has a finite number of values. So now on this chapter we concentrate on discrete random variable because it's finite numbers, finite countable and numerical numbers. And okay, so for example, number of eggs a hen lay per day. That's definitely a discrete random variable. It's finite number, it's countable, and it's a numerical number. Also, number of people attending the parade. That's also, although it's pretty large amount of number attending the parade, but it's still finite countable numbers. So this is what they call the discrete random variable. Finite countable numerical numbers. To put it in simple language. Finite countable and numerical number. Or numerical value. This is the essence of the discrete random variable. Continuous random variable has infinitely many values. Those values are associated with measurement on a continuous scale without gap interruption. So for continuous random variable like temperature, it's a typical continuous random variable. Temperature always occurs in a certain interval. For example, let's say it's from 20 Fahrenheit to 90 Fahrenheit. Something like that, and all these values are in between are possible, and it's given in a particular interval, right? And every number in the interval is possible. So you have infinitely many values from the interval. humidity, right? That's also an example of humidity. Humidity on any given day, it's a continuous random variable. Usually it's given in the interval with infinitely many values available. Now, random variable to follow the probability distribution, you need to satisfy two requirements. So we have numerical random variable x, and its value associated with corresponding probability, just like that example flip a coin case, flip a coin twice. So now the sum of all probability must be 1. Each probability value must be between 0 and 1 inclusively. So those two are requirements. So you get this random variable, following those two requirements, and that's what we call the probability distribution. And if you flip a coin case, you can list a table like here. We can create a table x and p of x. Here, x, we're looking at the number of heads. Count number of heads. If you look at it, we get 0 heads, 1 head, and 2 head. For 0 head is 0.25. For 1 head is 0.50, and for 2 heads is 0.25. We calculated from earlier slide, and as you can see, if you sum up all this probability, the total probability here is equal to 1. And each probability is between greater or equal to 0, less than equal to 1. Right? So this particular case is a probability distribution. That's how you make a determination of the probability distribution. Create a table, list all the possible outcomes. Okay, X is all the possible outcomes, and then the probability associated with each possible outcomes. Now this is probability histogram. If you create a histogram from the earliest example, right, from that flip coin twice. Then we have the table here. 0, 1, 2. So it's 0.25. and 0.25. So here we could create a probability histogram here. Let's say this is 0.25. This is 0.5. Okay, so we get a 0. This is 0. That's 1 and 2. Okay. Now the first we could use in the rectangular box. The first one is rectangular box like that. Okay. Second one is rectangular box with the maximum probability follow on the rectangular box. Okay. That's how we construct the probability histogram. And this one, probability histogram for number of Mexican American jurors among 12. Okay. So again, we just list all the possible outcomes with that probability from the table like this. Then you could create a probability histogram. And now let's take a look at mean, variance, and standard deviation of the probability distribution. Okay, so the mean equals summation of x times p of x. If you sum up all the product of random variable times the discrete random variable times the probability associated with it. The variance equals summation of x minus mu squared times p of x. And we have a shortcut formula, and typically we're going to use the shortcut formula. Variance equals summation of x squared times p of x minus mu squared. So find the mu, the mean, and then we'll be able to find a variance. And then standard deviation is the square root of the variance. So standard deviation equals square root of summation of x squared times p of x minus mu squared. Okay, so keep a note on those formulas, and we're going to use it later on. Now let's take a look at the expected value. The expected value of the discrete random variable is denoted by E. It represented the mean value of the outcomes. So it's obtained by finding the value of this. Sum up x times p of x. So the expected value equals summation of x times p of x. And now let's take a look at the example. The following table describes the probability distribution for the number of girls in 2 births. Meaning, so all the possible outcomes for 2 births could be boy, 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 girl, girl, boy, girl, girl. You can easily construct a tree diagram to find out all these possible outcomes, right? So, boy, girl here. Okay, following the tree diagram, you get a girl, boy, girl, girl, boy, boy, and boy, girl. Okay, and exactly matches with these outcomes. So now if you look at it, for number of girls, you concentrate on the distribution of number of girls. So you look at number of girls, could be 0 girls, right? Boy, boy is 0 girls. You have a 1 girl here, 0 girl. This one is 2 girls. Okay, so we have 3 possible outcomes, 0, 1, and 2. Probability, we have a quarter. 0 girls is quarter, 0.25. And then 1 girl is 2 over 4, 0.5. And then 2 girls would be a quarter again, 0.25. Now in order to find the mean, we need to create this column x times p of x. So you multiply x by p of x. So you get 0 here. 1 times 0.5 is 0.5. 2 times 0.25 is 0.5. If you sum up that, the total here sum up, so summation of, so mean here equals summation of x times p of x. Okay, so if you sum up these two, you get it 1. So that means mean equal to 1. Okay. In order to find the variance, we need to create another one using the shortcut formula. Okay, so we need to create an x squared times p of x. So in order to find that, you multiply the first column by the third column. X times x becomes x squared, and then carry over the p of x. So multiply x 0 by 0, you get 0. 1 by 0.5 is 0.5. 2 by 0.5, you get 1.0. If you sum up that, so this becomes summation of x squared times p of x. That's equal to 1.5. Then the variance sigma square equal to summation of x squared times p of x minus mu square. So that's 1.5 minus 1 square, that's going to be 0.5. So the variance equal to 0.5. Okay. By simply using the table, you can easily calculate the mean and the variance. Now the mean, we did it, summation of x times p of x turned out to be 1. Variance is summation of x squared times p of x minus mu square. That's 1.5 minus 1 square, that's 0.5. The standard deviation sigma equals square root of 0.5. That's square root. So it's square root of 0.5. So if you run it to 1 decimal place, turn out to be 0.7. Okay. So by creating the table from the earlier slide, we'll be able to calculate all of these outcomes here. mean, variance, and standard deviation. Calculate all of those. Now let's look at quickly review the expected value. Mu of this random variable divided by E, or mu of x, which represent the average value of the outcomes. Okay. Now let's take a look at this example from New Jersey Pick 3 games. So betting 50 cents and select 3-digit number between 000 and 999. If you get a number, you collect $275. Your net gain is then $274.50. Suppose you're betting 50 cents on the number 007. What is your expected value? Okay, so very important thing, we're going to create a table. If you look at this, you only have two outcomes, right? Either you win or lose. If you win, so this x value represents, if you win, you get net gain. If you lose, you have a net loss. Okay, so win, you collect $275, but you're already betting 50 cents, so the net gain here, x value represents a monetary reward here. That'll be $275 minus 0.5, 50 cents. So the net gain will be $274.50. And the net loss, if you lose 50 cents. So negative 0.5. Since it's lose, you put in the negative number. And the probability of winning. Okay, let's take a look at this. So you have to find a probability of winning. We need to see how many numbers are there, right? So we get it between 999, 000. Including the first one, that's 1,000 numbers there. Available, 1,000 numbers available. And only one winning numbers. So probability of winning will be 1 over 1,000. So it's 1 over 1,000. Turning decimal is 0.001. Probability of losing, so one winning numbers, that will be 999 losing numbers. So probability of losing will be 999 over 1,000. That turned out to be 0.999. Now you just multiply x and then p of x. Here the discrete random variable with the associated probability. So 274.5 times 0.001 becomes 0.2745. And negative 0.5 times 0.999. That's 0.4995. Negative 0.4995. So if you sum up that, that's the expected value. So the expected value equal to summation of x times p of x. You create a total column here, sum up that becomes negative 0.225. So here the expected value is negative 0.225. Okay. So what this expected value means is every time you play the game, you expect to lose 22.5 cents. This dollar amount. You expect to play the game, you expect to lose 0.225. Okay, that's the meaning of this expected value. It gives you average value of the outcomes. Okay. Identify unusual results is range rule of thumb. Okay, so range rule of thumb, most values should lie within 2 standard deviations of the mean. That's a basis for the range rule of thumb. So we can therefore identify unusual values by determining if they lie outside of those limits. So maximum usual value equal to mu plus 2 sigma, mean plus 2 standard deviation. Minimum usual value equals mean minus 2 standard deviation. And we find for families with 2 children, the mean number of girls is 1, the standard deviation is 0.7. So the maximum usual value here, so mu equal to 1.0, standard deviation equal to 0.7. So that's given. So maximum usual value will be 1.0. No, let me just add a formula first. So mu plus 2 standard deviation so that will be 1.0 plus 2 times 0.7. So that's 2.4. Okay, and then minimum usual value. So mu minus 2 standard deviation. So it's 1.0 minus 2 times 0.7. That turned out to be negative 0.4. If you look at all our outcomes, right? Outcomes, you see the 0 girl, 1 girl, 2 girl. As you can see, they all usual values. Okay. They all usual values. Getting 0 girl, 1 girl, 2 girls. Okay, they all usual values. And then find usual results, right event rule for inferential statistics. So even under a given assumption, such as the assumption that the coin is fair, that means probability of head and probability of head tail is equal to 0.5. So probably a particular observed event such as 992 heads and 1,000 toss of coin is extremely small. Okay, it's very unusual event when you get into 992 heads when you toss the coin 1,000 times. The assumption is probably not correct. And this probability definitely is not going to be 0.992, right? Probably heads, according to this particular event, is 992 over 1,000, which is 0.992. And this is definitely an unusual probability, unusual event. So you cannot use a 0.992 as a probability of head. That will be incorrect. Also, we can use other methods to identify unusual results. So unusually high if x success among n trials is unusually high. Of number of successes if p of x or more or less or equal to 0.05. And if the probability is very small, then it's probably not likely to occur. Also, it could be unusually low. X successes among n trials are usually low. For example, let's flip a coin 1,000 times. You're getting 990 heads. So this is, if you're betting on the heads, so this 990 heads will be unusually high. And also probability of x. Okay, so that's why this is unusual event. Also 10 tails. 10 tails is unusually low. Okay.